Hi, everyone, and welcome to Space Tech, building the next frontier of civilization. Space has always been driven by imagination, but civilization is built through systems that actually work. That means confronting uncertainty, autonomy, and the constraints of physics and economics. Today's panel spans those perspectives, from fundamental science to spacecraft automation to in-space operations. Today, we'll talk about where the biggest gaps remain, how autonomy is reshaping space systems, and what feels inevitable in space, even if it doesn't exist yet. So let's go ahead and get started. I'll start with some introductions. My name is Annika, and I'll be your moderator today. I'm a PhD candidate working in mechanical engineering at MIT, and I work in the intersection of robotics, perception, and planetary exploration. I focus on how intelligent systems build and share world models in extreme environments like on the moon and Mars. Jacob is the founder and CEO of Oligo Space. He's leading a team that brings together veteran engineers from NASA JPL and SpaceX with next-generation AI researchers from leading universities to build an AI-powered automated spacecraft design and manufacturing platform. Oligo works with governments, space companies, and non-space enterprises to move from mission concepts to operational satellites in months, delivering custom, capability-driven space systems through a software-first, forward-deployed model internationally. Priya is a theoretical astrophysicist and professor at Yale University. She is internationally known for her work on dark matter, black holes, and the large-scale structure of the universe. She brings a fundamental first principles perspective on how we understand and model the cosmos. Joe is the co-founder and president of Rendezvous Robotics, a company that's focused on in-space operations and servicing. His work addresses what it actually takes to deploy robotics reliably in orbit where failure isn't an option and autonomy is essential. So let's go ahead and get started with some questions. First off, when we talk about imagination becoming action, what is the biggest gap you see today between what we can imagine in space and what we can actually build or deploy? Jacob, you can start, and we'll just hear everyone's perspectives.
I think for me, I grew up with a lot of the space movies. I think growing up with Interstellar kind of makes you have very high expectations for what the space industry is. But I think one of the cool aspects of having all those movies, still going back and watching all the Star Wars films, seeing every single other sci-fi film, I think when it comes to action, I think we just have to look back at those types of movies, all the fiction that we define as fiction, and understand that all that stuff is actually happening in real time. So.
Well, I guess I'm going to bring us back to reality.
Yeah.
Those are movies, and while it is true that is one of my favorite films, Interstellar, in the making of Interstellar, no physical laws were violated. But I can't say the same for all other space movies, comic books, and so on. So I think that when it comes to space, imagination is a very powerful motivator for really getting us to do work and to get us to actually explore and get there.
So I'll try to bring together imagination and practical too. So I'm an engineer, so I like to build things. So what's holding us back from our imagination is in space. One big thing is that everything that we send to space has to be folded up to fit into a rocket, which is a tube. And it's a limiting and actually an absurd constraint on what we can build in space today. That's what Rendezvous Robotics is looking to break through that constraint. And instead of building satellites or spacecraft on Earth and then folding them up to fit into a rocket and then hoping that they unfold once they get to space, we're going to send modular pieces to space using MIT developed technology to assemble spacecraft in space to whatever you can imagine and whatever your mission needs. We can build that.
Cool, great perspectives. I've actually worked a bit with deployables, and it's pretty challenging. You think it would be easy for something to just open up in space, but it's one of those challenging engineering problems.
Well, the James Webb Space Telescope, though, was stunningly beautiful, but there were lots of tense moments
Yes,
when
and
in
many
its deployment,
single point
many
failures
single point failures
possible. Right?
Yeah.
Yeah, I mean, and that brings up kind of a great bridge into the next question, which is how do fundamental scientific models of the universe, of physics, of uncertainty translate into real world engineering decisions in the cases where systems have to operate autonomously, far from Earth, where if something doesn't deploy, we can't just go send an engineer or an astronaut very easily to fix it.
Unless you're Jeffrey Hoffman, who can just go fix the
Can
Hubble
fix
Space
anything.
Telescope.
Yeah.
Yeah.
No, I think that there are several other important constraints that we have to operate under. I mean, I think one of the important things has been sort of the anatomy of missions, and they have to be foldable, origami-like in order to work. But I think there's a very fundamental physics problem that we have not yet solved, but we will solve, and that has to do with radiation resistance. The fact that we don't yet have the capacity, I mean, we can't be using lead for obvious reasons. And I think it's a fundamental problem that we know needs to be solved, can be solved, but I think we need to put more energy into that one.
Yeah, I agree. I think radiation, there's some unique things about space, right? So in space, there's extreme temperatures, it's a vacuum, and there's higher radiation than we're used to on Earth. So we have to plan and design around all of those unique aspects. I think another one, like there's laws of physics that are not ever going to be broken, like the speed of light in communications, particularly for deep space exploration. I used to work on deep space exploration spacecraft, including a mission called OSIRIS-REx, which is a NASA mission to go to the asteroid Bennu. And it was a long, tens of minutes time delay to talk to the spacecraft. And this spacecraft had to rendezvous with an asteroid and actually encounter and touch the surface, and then collect a sample and then come home. It's not a mission that you could, steer or use a joystick for because of the fundamental, it was far, far away, in the solar system. So we had to design autonomous systems to overcome that time delay, and it had to be able to adapt on its own. It's, simple autonomy, because this is not anything, like some of the other AI we're talking about here in Davos, but it was effective, and I think it shows that we can start working our way towards more autonomous systems.
I think in our case, we work a lot with physical modeling of astrodynamic phenomena. You see LEO, MEO, and GEO. And the funny part is that a lot of these are based on models of data collected, in some cases, like decades ago. So I think the one big thing that we're missing when we're trying to create kind of a digital twin of what that orbital environment is how do you actually get 24/7 monitoring of what the orbital weather conditions are? How are you going to get proper rating and measurements on what your pressures are that affects the ADCS system of your spacecraft? So I think I'm looking forward to a couple companies I know some friends in the UK starting and working on, which is how do you actually get a proper, accurate model of the orbital environment outside of the models we've currently been using in simulations here on the ground.
Yeah, I think it's really interesting that you guys brought up radiation, which I'm sure fit into these models as well. And I was curious if you could elaborate a little bit on how that plays into your research or your work. I think a lot of people that aren't as familiar hear radiation and they think, oh, that'll be challenging to send astronauts to Mars because people might get cancer from radiation. But when you're working in different systems, maybe that don't involve humans or that involve humans and robots in space settings, how does that impact design decisions you make?
Well, I guess the first thing is that when we're talking about, much of my own work, broadly speaking, involves the understanding the effects of the interaction of matter with radiation, because all celestial cosmic objects emit radiation in some wavelength or the other, and they have very particular specific physical processes that release the kind of radiation and the span in the electromagnetic spectrum that the energy comes out in. So I think the crucial question, aside from tissue damage, which we know even at the International Space Station, when the twin study was done, we know that the lengths of telomeres get, the Kelly twins. So we know that, for human tissues, we know that's a problem, but we also know that for equipment, it's a cause of degeneration and disrepair. And it could also impact electronics, right? So it's a big fundamental problem that we do need to solve. And I think the first thing is understanding, and as Jacob said, redocumenting LEO, GEO, NEO, what are the kinds of radiation levels and the fluctuations in those levels that can be expected. I think documenting that, updating, and having a full sort of database then will allow us to do sort of libraries of models so that we can simulate those environments. And I think in particular, right, if we want to go beyond, just rovers, for example, if we want to do some kind of habitat type things, or at least experimental, I think that we also need to understand how to operate in that gravity. I think we cannot, gravity is the final arbiter, and the fact that, the gravitational pull is significantly different is something that we also need to simulate in terms of structural work, even autonomous assembly that we would have to do there. Right.
Yeah, I'll talk a little bit about electronic systems and radiation. Priya started talking about this. As a practical matter, there's really three ways to mitigate radiation in space. We can bring extra processors or extra computers so that if one has a problem, we could go to the other, or we can have 3 computers that vote, and you want to only go with you can determine the right answer that way. You also do shielding, which is you can do for humans as well. It's really one of the only solutions. Bringing extra humans is not a appropriate mitigation for radiation.
Yes.
We can bring extra chips. So you can shield the chips, or you can do operational constraints. So, your home computer, you don't reboot it that often, but if you expect radiation to be affecting your computer, you could just plan on it to reboot every few seconds and design your system to just be tolerant of that radiation.
And I think you need the calibration. The calibration is
Right.
really, really important, and that's where, as you pointed out, getting data, right?
Yeah, it helps to know what to expect, because otherwise we have to over-design. Right.
Yeah, totally. I think it's really cool because one of the people flying on our first mission going up next year is someone trying to test both a way to write flight software that can accommodate for any of these upset events, but also a radiation shielding made out of both a composite, polymer, that you can coat any structure, electronics, PCB in that's 3D printable. So I think it's cool. There's multiple companies pushing forward with this, and it's kind of like an interesting implementation problem, because these are things that now need to be represented in the proper, vibe testing simulations. How are you meshing something like a organic polymer around your spacecraft, around your electronics? I think those are some interesting problems coming up now that people are really trying to insert these solutions into the design space, which is a cool thing to see.
Yeah, so, looking forward into the next decade, and feel free to have your answer to this question be radiation shielding or something adjacent. But I'm curious, what is one capability in space robotics or autonomy or infrastructure that feels inevitable but isn't there yet, doesn't actually exist right now?
I think it would be radiation shielding for me. But I think that, as I said, it's a hard problem. And I think we can do some brute force solutions, but I think it would be great to have an elegant solution. Because I'm a physicist and I'm always looking for a really cool, neat way that's scalable, that's not very expensive, that you can use for radiation shielding, both for our equipment as well as for any potential humans.
Spacecraft today, we build them, like I said before, we send them to space, and then what you have is what you have forever. So what I think a capability that we need and that I'm excited about is modular spacecraft that can be changed or upgraded once they've been sent to space or serviced. So I think this is capability that will have really lasting and important impact on the types of missions we can do when we don't have to have, we're not stuck with what we send up to space. We can add to it, we can change it based on the mission. Modularity is an important way to achieve this by building spacecraft that have certain systems that can be upgraded, changed, or reconfigured.
I think seeing the risk tolerance for missions going from a flagship type of spacecraft at JPL going into the first private mission going to Venus led by MIT as one of the primary PIs in Rocket Lab as the main integrator. I think I'm so excited to see that you no longer have to build a Class A flagship mission to go to some of the outer parts of the solar system. There's no reasoning with radiation shielding. The dynamics are a solved problem. It's just what are the primary reasons why funding will go in that direction? And there's a lot of billionaires now that are willing to kind of push these science questions themselves. So seeing kind of Smith Futures do it first, I'm excited to see kind of private industry, nonprofit industry using these as education channels to now push forward what would be more private science-directed flagship missions that are orders of magnitude cheaper.
Well, and they can take more risk, maybe.
Yes,
I
I
think
think
that's
they can
important.
tolerate a lot more risk. And I think one of the exciting things with the recent announcement with the Schmidt plans is that all the data will be open and immediately available. And I think, but as an astrophysicist, I think the flagships are wonderful too, because I mean, they take a long time, but the number of science questions that, the data from one really well-planned mission. Of course, the flip side is that the technology gets outdated if it takes 20 years of planning to get it up there. But the kinds of science questions and the questions you didn't even anticipate, that kind of data deluge allows you to address, right? I wouldn't want to give up the flagships. I want them too, right? I want them. And
I'm
All
a
of the
huge
above,
fan.
yeah.
I have if you look at my backpack, I have a bunch of the flight tags from Clipper, Psyche, everything. I love them so much, I just want more of them,
I'm glad you brought up data too. I have a couple questions about autonomy in space, and I'm curious that as we push towards having more of these autonomous systems in space, what do you feel like we need to trust more? Is it the models that we create, the data, or systems' ability to adapt when both are wrong?
Do you want to go first?
Well, maybe to answer in a little bit different direction. So the Orion space capsule, which is designed to go into deep space, there has to be a level of autonomy there because we're not always going to be able to phone home for help, those astronauts, because of the time delay like we talked about earlier. So I think for deep space human exploration, we actually need to trust the people more, and they need to be able to trust their systems really with their lives.
And just a follow-up question, since you work in a lot in the autonomous space, do you feel like we're over-romanticizing autonomy in space, or do you think that is there anything that you feel like we're avoiding admitting is actually still too hard right now?
No, absolutely not. I think what we've gotten good at over the last wave of sort of small sat development is rapidly adopting terrestrial technologies like commercial microelectronics. We are now really good at bringing those technologies into space faster than we were before. This is not the day where the space shuttle flew with ancient computers, right? That's not, satellites and spacecraft today don't have that same problem. We can bring that technology in, test it, and incorporate it much quicker.
Yeah, and I think that a lot more coordination, especially with a lot of private companies and philanthropists and billionaires pumping money into space exploration, I think it would be really good for sort of a platform, kind of, a more formal public-private partnership kind of thing that is more organized and kind of coordinated, so that we are trying to kind of optimize the kinds of questions that I keep coming back to the fundamental science, because I think we're trying to learn something that we know what we want to learn, as well as things that we don't even know that we're going to learn. So I think coordination, I love all this energy that's happening, but it would be nice to have much more coordination with the various autonomous missions, test flights, everything that's happening.
I think I've worked pretty closely with the Space ROS team, and if you look on the ground, the robotics development, a lot of companies use ROS either in a real-time operating system or a non-real-time operating system. And I think flight software has always been a really big black box, even internal to companies. If you go to Rocket Lab, if you go to JPL, some of them don't have any idea how the flight software works. It's the people that do flight software, they know flight software, and they're getting access to the computer later than they actually should be. So I think that automation aspect, in order to really push forward all the algorithms that are inherently already existing in either simulation environments, it's really closing the loop on being able to push this in the hardware that is limiting us in orbit. You can't run a lot of these algorithms for sensor fusion and position estimation using the existing compute modules we're even using on our satellite. We're getting to the point where we can deploy some of these Jetsons, some of the higher computers, using multiple computers, like we were saying. I think that's the big thing.
More open sharing, right? Sharing of codes that are currently available.
Yeah, so F Prime is a really awesome flight software framework where we're collaborating with JPL to really open source what the architecture is going to be for implementing some of these higher autonomy maneuvers. How do you go from operation modes into real kind of commanding that you would see at the subsystem level? So I think that big push to not having to write a state estimation controller from scratch all the time, I think that's going to make a really big push forward to people really advancing the autonomous function, now that the base functionality is a solved problem.
Yeah, I love the idea of more modularity, in the spacecraft design itself, but also in the flight software. And I would love to have a replacement for ROS that is not ROS 2. So, all right, we're wrapping up on time here, so I'm going to ask all of you just one last question, and that is what excites you the most right now? Is it the moon, orbit, or deep space, and why?
I know my answer is the moon. I think what we're going to see here just in a few weeks with the Artemis 2 mission is super exciting. It's going to be the first time humans have gone into lunar orbit since the Apollo program. The flight profile that they're flying is going to put the Artemis astronauts farther from Earth than any humans have been before. The SLS rocket is on its way out to the launch pad as we speak today, so we're going to have a really exciting time in exploration over the next many years as we see the Artemis program explore and develop the moon.
I think for me, it is deep space, probably predictable, right? And I think also big fan of unmanned missions as well with a full suite of instruments. I think that the combination to be alive at a time when 3 flagships, the Hubble Space Telescope, the Chandra X-ray Telescope, and the James Webb Space Telescope, are all on and are able to look at the same patch of sky, and especially the James Webb, allowing us to peek back to the start of the formation of the first stars, the first black holes. It's been absolutely thrilling to see the science that's coming out of it, and I think I would want a lot more of that.
Yeah, I think I'm team deep space for sure. I think a lot of the bespoke spacecraft that we're getting approached to build, it's like the same complexity exists once you leave the standard orbits that a lot of satellites are functioning in now. And once you start breaking this barrier of like satellites only exist in LEO, MEO, GEO, once you start building this single infrastructure to pump
L2,
out,
right?
yeah,
L2.
like your constraints now become more common because you're planning for an environment that otherwise is kind of already on that edge of extreme. So when you already start kind of building in that domain, there's a lot of interesting stuff that can come out of it.
Cool. Well, thank you so much for your time and for your insights. Let's give the panelists a round of applause.